And this is the solution and explanation to question 6 on the Physics 211 practice exam. In this case, we've got a trebuchet here throwing water balloons at the SU quad. And we've kind of got a mid-flight measurement. So somewhere in the middle of the trajectory of this water balloon, we have measured it at this spot to be 68 meters above the ground with this velocity, 42 meters per second, directed at 20 degrees above the horizontal. And this is all you know, right? You have a snapshot in time giving a position and a velocity, and you're supposed to find out where the water balloon was launched from and where it will land. So in this case, we have a sort of a simple question to answer. First thing to do is pick a coordinate system, pick an origin. Here it's not entirely obvious, right? Because we don't know where the water balloon started, we don't know where it's heading, but we do know where it is. And to avoid negative numbers as much as possible, I'm going to pick an origin at this point. The origin will be here, underneath the water balloon where it was measured. And then with that coordinate system, the position and velocity relations, x of t is v naught xt, because the initial x position is 0, and y of t is v naught yt plus h minus 1/2 gt squared. And we might as well go ahead and put in the trigonometric functions that these are equal to. So this is v naught cosine theta times t. This is v naught sine theta times t plus h minus 1/2 gt squared. And one thing to note is if this point is t equals 0, it was launched before t equals 0, right? It was launched sometime in the past from where we've made our measurement. So we can anticipate, we can sort of guess what will happen here, right? We're going to need to use the quadratic formula, and one of the roots for the quadratic formula we expect to be negative. That's fine. Often, a negative time means something happened in the past, and it's the non-physical solution. But here, the negative time solution actually is physical. It tells us how far in the past the object was launched from. So we can, as always, frame our question in terms of our mathematical variables. Since the ground is y equals 0, this point is our origin, we can say, what is x of t at the time that y of t equals 0? This is kind of the standard thing that we often do, but cooked up in a way that both solutions are meaningful and one of them has negative time. So the purpose of this question, of course, is to require us to think critically about what the roots from the quadratic formula mean. So let's find the time that y of t equals 0. So I've got this equation. I say 0 equals, I'm just going to write the terms down in the conventional order now, 1/2 gt squared. Actually, I'm going to color code them. I want to do this for a reason. To kind of make it clear how the quadratic formula is going to work for us. So I have 1/2 g with minus sign times t squared. Then I have the velocity term plus v naught sine theta times t. And then I have this term plus h. And of course, these coefficients that I have color-coded are the a, the b, and the c in the quadratic formula. Now, we kind of like to do this with the leading coefficient positive. So I'm going to flip all these signs around. I'm allowed to do that by the rules of algebra. And then now I can write down the quadratic formula. T equals minus b, so that's v naught sine theta, plus or minus the square root of b squared, so v naught squared sine squared theta, minus 4ac, which gives me, so that minus cancels that minus to give me a plus, 2g times h. And then all of this is divided by 2a, which is just divided by g. Now, so I'm not punching calculator buttons on camera. I've already pre-computed what these values are. I ran the quadratic formula before I put this up on the board, right? And this gives us times of minus 2.52 or 5.39 seconds. But what I wanted to do was I wanted to find x of t at that time. So x of t is v naught, not sine theta, cosine theta. V naught cosine theta times t, which comes out to be either minus 99.5 or 212.9 meters. So these distances are quite large, right? But we're imagining a snowball throwing machine throwing snowballs from Oakwood Cemetery to the SU quad. So this is a fairly long distance, right? The values we've gotten kind of make sense. And one of them's negative, right? This one's negative. This makes sense. Our snowballs were thrown from, not snowballs, water balloons. Our water balloons were thrown from a point to the left of the origin at a time before when our photograph was taken. Right? T equals 0 is here. This point is t equals, what was it? Minus 2.5 seconds. And then d2, the distance where they will land, is 212.9 meters. And they'll land over here 5.3 seconds in the future. So 5.3 seconds. 5.4 if we're rounding. So I've answered the question. With one snapshot measuring the water balloon's position and velocity, I know both where it was launched from and where it will land, and when it was launched and when it will land. So this is the solution to this question, but this is kind of, I'm speaking to any ROTC students we have here. This question was actually inspired by something in military science. So those of you who have been following the war in Ukraine know that a technique called counter-battery radar has been extremely vital for the Ukrainians. It's been a capability that the United States has provided as military aid to the Ukrainian army that they're making very, very good use of. The idea is that rather than taking a photograph of a water balloon, you receive a radar return from an artillery shell while it's in the air. So if someone is firing artillery at you, not just a water balloon in this innocent example, you can make a measurement of the artillery shell's position and velocity using radar. And by doing this sort of mathematics, modified slightly for things like wind resistance, you know, just from this mathematics, where the artillery shell will land and where it was fired from. And if you can do this mathematics very quickly and communicate it to your own artillery, you can engage in counter-battery fires. You can fire back at whoever this is, without ever seeing them, simply by making a radar measurement of the artillery that they are shooting at you. So this is a capability that's allowed the Ukrainian army to defend itself against the Russian invaders, basically by firing more accurately back at them. So this question, while it's kind of a whimsical example, is inspired by something pretty serious. So that's the solution to question 6. And my computer has gone to sleep. I have to log back in order to stop the recording. There we go.